calculus context.
So the 2.1 is in the calc book.
2.1 is in the calc book, yeah. Get rid of the extraneous lines. Okay, so let's say I'm going on this trip, and I'm going to start at time equals 0. So it doesn't matter what time on the clock is. I'm just going to set my stopwatch, and I'm going to push the stopwatch at 0, and I'm going to call where I'm starting 0. That's everything is measured with respect from where I start. Now I'm going to go for 4 hours, and I'm going to find that I've traveled 200 miles. So what's the average speed over this trip? I mean, this is you can do this in many different formats, right? If you do this in almost a middle school format, you say 200 divided by 4, and you get 50 miles an hour. With what we have defined as the rate of change, we take d2 minus d1 over t2 minus t1, and so we get 200 over 4 equals 50 miles per hour. Okay, so that's your average trip speed. Now let's say we're writing down all of our times and our distances, and we're going to say now, all right, at 2 hours, we've gone 80 miles. Okay, so then we can ask the question, what is the average speed for the first 2 hours and the last 2 hours? Okay, we just do the same thing. We have different numbers involved. So for the first one, I'm going to say the difference in the distance that I've done is 80 miles minus 0. The difference in time is 2 hours minus 0 hours. So for that first 2 hours, I'm traveling at 40 miles per hour. And then for the second part, the delta D over delta T is going to be 200 minus 80, because then I've gone 120 miles, again in 2 hours, and I've gone 60 miles per hour. So for my overall trip, my average is 50 miles an hour. For the first part of the trip, my average is 40 miles per hour. And the last part of the trip is 60 miles an hour. Okay, so I'm going to fill in a few more values here. At hour 1, I'm at 30 miles. At hour 3, I'm at 135 miles. So what's the speed at 2 hours? Now, when you're driving, imagine you're looking at your speedometer, and that tells you what speed you're going. Now, it doesn't really tell you at the average speed, right? I mean, you can calculate the average speed by looking at it exactly the way that we did. But really, your speedometer tells you what is your speed at any given time. Now, with this data, can we figure out exactly what speed we're going at the 2 mile mark? We can't really, right? We can probably make an estimate or so, or we could figure out where it needs to be. But we don't really have a way to look at the particular values. So let me just reproduce that table. And I'm going to introduce reintroduce some symbols that we talked about last week, that we're going to talk about time and distance with respect to where we are. The point of interest is going to be at 2 hours, where we're at the 80-mile mark. So I can look at d as a function. So d at t is 80, right? D at 2 hours is 80. And then instead of looking at the two differences in the times, I'm going to call this a delta t. So one way to look at this is when you're at the 2 hour mark, what is the difference in time with respect to where you are at 2 hours? And so if t2 minus t1 is delta t, I can say, okay, rearrange that. My t2 is 2 plus delta t. So if my delta t is where was I an hour ago, then I would say 2 minus 1, that's at hour 1. Or where am I going to be in 2 hours? My delta t is 2, so I take my current time, which is 2, and add 2 to it. So this t plus delta t concept is a way to address differences in time with respect to the main time that we're interested in, okay? And so that's kind of the big idea about using these. So if I were to rewrite my table and say, okay, the time that I'm most interested in is hour 2, my delta t for that table is going to be everywhere from -2, -1, 0, 1, and 2. And so if I take my t plus delta t, I'm going to get my t2 right back. So that's my original table, 0, 1, 2, 3, and 4. And so if I look at my function then, is not necessarily just at d at whatever t. We're talking about d at t, where t is the 2 hours plus delta t. I get my original time, my original distances back. So it may seem like it's a little bit convoluted at this point, because why are we introducing this? But if we're interested in a particular value, what we don't want to do is confuse it by looking at two different values of t. So I'm just taking this perspective that at 2 hours, I'm at this place, and I'm thinking ahead and I'm thinking behind. And the delta t tells me how much ahead, how much behind, and then the d at t plus delta t is where I'll be at those times with respect to those values. So I'm going to define the average speed just the way I've always done. It's the difference between where I end up and where I start. And so if I put it in this kind of the symbols that I've just defined, I'm going to get this thing that's going to be kind of like your best friend in terms of rational functions for the next few weeks. This is called the difference quotient. Okay, difference because it's how much different in place and time you are. The quotient because it's the ratio of the two. So it's in fact a good definition for average speed. And I'm going to indicate average speed by making S with a bar over it. And the bar means that it's average. So if I look at, all right, what's my average speed over the last 2 hours? All right, so I stick in -2 for my delta t, and I calculate, well, 2 hours ago I was at 0. My current place is at 80, so I take the difference there, divide it by -2 because it's 2 hours ago, and you get 40. This is exactly what we got on the previous chart. An hour ago, I was at mile marker 30, and so I calculate that to be 50 miles per hour. Similarly, an hour from now, I'll be at 135 miles, and my average speed over the next hour will be 55 miles per hour. And for the last 2 hours, it's what we calculated as perhaps the third calculation on the previous chart, where my average speed for the next 2 hours will be 60 miles per hour. So you see how this delta t notion really talks about time pretty much the way you talk about time. I mean, you don't, when it's 9 o'clock or just barely after 9 now, we talk about where you're going to be in 5 minutes. You're going to be in the hallway, right? We don't really talk always about particular times. We talk about time differences between now and when we're going to be at some other place. So I'm going to leave you with this notion. What's my average speed, or what's my particular speed right now? If I put my formula in there, I have d2 minus d1 is just 40 over 40, or 40 minus, excuse me, 80 minus 80. And the difference in time that I have is going to be 2 minus 2 is 0. So my speed is 0 over 0. That really doesn't have any meaning. And so what we're going to generalize this into is we're going to have the average rate of change, and this is the slide that I'll start on Friday. The average rate of change over some value of x is going to be that difference quotient. And then the instantaneous rate of change at the value that we're interested in is going to be the limit as that difference goes to 0, where we have this difference quotient. So the notion here is that we're going to introduce something new called a limit. And so the limits that we're going to take are either going to be as x approaches a value, or x approaches 0, or x goes to infinity, you know, things of that sort. And so we're going to be interested in the functions and how they change over the course of their domain and things of that sort. So most of what we're going to be doing in the next week and a half is going to be looking at polynomial functions, power functions, rational functions, and see what their instantaneous and long-term behaviors are in the context of our toolkit functions. And then we're going to introduce how we actually calculate a limit. Okay, so I'll start here on Friday. Yeah, sure, I'm just going to